Hi, my name is William. I'm a PhD research student at the Welding Engineering and Laser Processing Centre at Cranfield University, and this is a presentation on my research towards the selection and performance of additive manufactured superalloys for high-speed flight environments, which is sponsored by DSTL and the Ministry of Defence in the UK. So the aims and objectives of my research is to select appropriate alloys for both the high-speed flight application and for welding. So the application will be for a highly stressed component at service temperatures between 1000 and 1200 Kelvin, and at 1200 Kelvin will be for components in the propulsion flow path. The alloys must also be weldable, so we can use them in the wire plus arc additive manufacturing process, which is just to prevent welding defects such as strain edge cracking occurring, and selecting alloys that are less susceptible to that. So then we're going to deposit the selected alloys using the WAAM process, which is going to be a plasma arc welding process in an oxygen controlled environment. We also want to investigate the mechanical properties of the WAAM material, which we're going to be using room temperature tensile and hardness testing to do that. And we also want to understand the effect the WAAM process has on the alloys, which we'll then compare with literature data to get a better idea of how these alloys are performing. So what is WAAM? Well, WAAM is the wire plus arc additive manufacturing process, and is a combination of an electric arc as a heat source and wire as the feedstock. So here we have our substrate plate, which is what we're going to be using to weld onto. In my case, it was an Inconel 718 plate and an electrode, which is housed inside our plasma welding torch. And we also have our wire feeder, which is going to feed wire to our welding torch, which is our feedstock. And we also have our enclosure, which is housing our argon gas in the atmosphere. And we have our torch gas as well, which is also argon, which is providing some additional shielding during the welding process. So now we're going to start welding, and as you can see, the blue area on top of the welding plate is representing our welded bead. So that's our first welded layer. The torch will flip around, start welding again, and the wire is always fed in front of the welding torch. So here we have our second layer. And then we'll fast forward and we'll start welding again. So here we have a what we call a WAAM wall, which is a block of material that we are then going to extract samples out of to be tested. So now we're going to move on to our alloy selection for high-speed flight environment, which includes the alloy ranking method. So 73 alloys were ranked in total using literature data from a variety of different sources. So the broader data set comes from the following sources. So the Superalloy Technical Guidebook, the MMPDS document, which is a military document that is now open source, which has a lot of information on high temperature metals. Then we have the Nickel Development Institute's number 393 document, which is very good for some nickel alloys, and the materials property database for selection of high temperature alloys, etc. It's quite a long title. And we also have the manufacturer data sheets as well, where it wasn't available in the above sources. So we have 73 alloys in comparison in total. So more points equals better performance. So as you can see the table on the right, we have lots of different categories and temperatures at which we're going to be ranking the alloys. So to start with, we have ultimate tensile strength, tested at two different temperatures. So the first is 1000 Fahrenheit and 1400 Fahrenheit. So all of these temperatures are actually converted from Fahrenheit. So then we have yield stress as well. So the same two temperatures. Then we have weight efficiency at the same two temperatures. Then we have buckling efficiency just at 1000 Fahrenheit, as well as coefficient of thermal expansion, elastic modulus, and thermal stress, which we'll get onto a bit later. And we also rank the susceptibility to cracking, which is an estimate based on the aluminium and titanium content of the alloys, which isn't ranked as a temperature. Oh, and yeah, all the temperatures are converted from Fahrenheit, as I said. So missing data points were estimated where possible via extrapolation and interpolation, and then average values as well. And we use simplified equations where possible to estimate the performance, just to simplify the process. So first we looked at our strength comparison of all the alloys, which used the broader data set. So on the left you can see the MMPDS document, and on the right is the data from the Superalloys technical guide book, which actually does have more alloys than the MMPDS document. But what the information that the MMPDS does have on the alloys that are included is quite detailed. So you can see the solid lines are representing UTS for the alloys, and the dotted lines are the yield strength of the alloys at obviously different temperature ranges. So the top alloy that actually comes out is Inconel 718. It's at intermediate temperature ranges, and as we get high into the increasing temperature ranges, we start to see 718 drops off, and Rene 41 kind of takes over from there. And then as you get even higher in temperature ranges, so now looking at 1700 Fahrenheit, alloy 188 will start to take over from Rene 41 as the leading alloy, which you can see right at the end here. So then we looked at weight efficiency. So we define weight efficiency as a function of UTS and density. So a higher weight efficiency is preferred for the application. So you see Inconel 718 again, it's coming out very good at sort of intermediate temperatures, and then we have Rene 41, which is getting good at the kind of high end, and then 188 again is coming out top at the real high end. Then we also looked at buckling efficiency, which we defined as a function of elastic modulus and density. So a higher buckling efficiency is preferred as well. So as you can see, it's a very similar story. We have Rene 41 is coming out at the top, Inconel 718. It's not far behind, but not quite as good as the intermediate temperatures. It's kind of more of a middle ground in this comparison. And then 188 is very constant throughout. So we also looked at the coefficient of thermal expansion. So a lower coefficient was preferred for the application. So at the kind of near the bottom we have Rene 41. Then we have 188, which again is a very straight line, very constant throughout. And we have 718, which is kind of going through the middle again, not too much difference from the other graphs. So we also looked at the elastic modulus of the alloys. So a lower elastic modulus is preferred, but not too low, so we're going to get more brittle type fractures. So we're looking more of a mid-range point in this category. So we've got Inconel 718, which is the more middle ground, followed by Rene 41, which is mid to high as you come through the range, and then starts to really dip off in its elastic modulus as it gets to very high temperatures. And then you've got alloy 188, which is again is very straight line throughout. So we also looked at the thermal stress, which we defined as a product of the coefficient of thermal expansion and the elastic modulus. So we did prefer a lower thermal stress for the application. And as you can see, 188 comes out really quite high throughout the temperature range. And then you've got Rene 41 and 718 kind of in the middle. And they swap places again when they get to higher temperatures. Another interesting alloy to look at in this comparison is Inconel 625 as well, which has a very interesting pattern. So here's a ranking table. So this is the broader data set, and the alloys are ranked and totals are given in this column. So the top performing alloy now, and this is without considering how weldable the alloys are at the moment. So we have Rene 41, which is right at the top, followed by a few other alloys, and then we get to the other alloy we're interested in, which is 718, which is kind of the bottom middle at the moment, not looking too great, and then 188, which is the cobalt based alloy, which is right off the table at the moment. So then we look to the weldability of the alloys to rank the alloys in their susceptibility to cracking. So to start with, you can see this dotted black line, which is representing our susceptibility to strainage cracking line. So everything above this line is going to be more susceptible to strainage cracking, and everything below the line is going to be less susceptible and hence more weldable. So we rank them on their distance from the line. So alloys under the strainage cracking line are preferred for weldability concerns. And so the top alloy we got was wasp alloy, which is pretty much on the line, followed by Inconel 597, which is this alloy, which is just over the line a teeny bit. And then we have mnemonic 942, which is just under the line up here. Rene 41, which is slightly over the line. And D979, which is this one here, slightly over the line. So here's the alloy ranking table again. So now we're going to remove the less weldable alloys. So that was all of the alloys that were significantly above the cracking line. So we're going to get rid of those, and then we come up with this table. So again, Rene 41 comes out quite good because it wasn't significantly over the line. And then we have 718, which has moved up quite a bit in the table now, which is looking quite good, kind of more of a middle ground. But we still have the cobalt based alloy, which is Haynes 188, which is off the table still at the moment. So we selected 3 alloys for the continuation of the project. So we went with the top performing alloy, Rene 41. We went for 718, which was a good middle ground, lots of data for comparison, and has good performance at the intermediate temperature ranges, as we saw earlier. And then we chose Haynes 188 as it was one of the best performing cobalt based alloys and has high strength at 1500 plus degrees Fahrenheit. So now moving on to the experimental method. So we'll look at the WAAM setup. So we're going to be using a symmetrical WAAM wall building process for this experiment. So here we have our enclosure, which is holding our argon atmosphere, and behind us we have the welding power supply. And if we zoom in a bit more inside the tent, we have our wire feeder, our welding robot, our part rotator, which is going to allow us to build on both sides of the substrate plate. And then if we zoom in on the head of the robot, we can see where the wire is coming in, which feeds directly to the torch, the robot, the part rotator, the substrate plate, which is this whole plate which we're going to be welding on top of. We have our plasma torch, which is going to allow us to build our WAAM wall, which is what you can see on top of the substrate. And we have our jig, which everything is attached to. And our inner atmosphere is, of course. So here's a quick video of the process that I used. So the robot is going to move up to allow the part rotator to rotate through 180 degrees for us to get to the other side of the substrate. And when we get to the other side of the substrate, the robot is going to come back down. It's going to turn around and go down to the starting position, and the main arc is going to come on, and the wire will start feeding. So as it's moving along the substrate, it's going to be feeding wire and depositing that to form your part. So the wire is always fed in front of the torch as well. So the benefit of depositing on both sides of the substrate is actually to cancel out some of the residual stress that you get from depositing the alloy onto the plate. And it also helps speed up your production time, makes it much more productive as you finish welding on one side, your cooling can take place on the other side while you're continuing the process on the opposite side. It's actually very good for increasing productivity. So when we get to the end of the plate, the main arc is going to turn off, and then the robot's going to lift up again. And then we're going to go to our cooling time. So for this process it was a 90-second cooling time. So now the robot head's going to lift up again. It's going to allow the part rotator to turn over again, and the process will just continue from there. So here you can see the finished products. So these are the WAAM walls that we built. So we got Haynes 188, got Rene 41, and Inconel 718. Looks very similar to the other two, but there wasn't enough room in the slide to put it. But we have very similar deposition rates, slightly higher in Haynes 188, slightly less in Rene 41, and less still in 718. But there's not a great deal of difference, and they're very similar processes, being quite similar materials. So we also heat treated the samples. So Inconel's 718 samples underwent a heat treating process of 1 hour at 970 degrees Celsius, followed by water cooling, and then aging at 8 hours at 718 degrees Celsius, followed by furnace cooling, and then a further 8 hours at 620 degrees, followed by air cooling. Then Rene 41 went a solutionizing treatment at 4 hours at 1065 degrees Celsius, followed by air cooling, then a further 16 hours at 760 degrees, followed by air cooling again. And then Haynes 188, which is not an age hardenable alloy, just underwent 2 hours at 1100 degrees Celsius. And on the right you can see Rene 41 air quenching post its solutionizing treatment, which is a nice picture. So then we did our mechanical testing. So we did room temperature tensile tests. So as you can see from the graphs, in blue you can see the wrought strength, which is the data from literature, and in orange we have as deposited. So that's material that was just extracted and didn't undergo any heat treatment. And then we've got our heat treated samples, which is the WAAM material which has been heat treated, which is in grey. So if you look at UTS here in this graph, you can see quite a big difference between the wrought strength and the as deposited strength. And then when we heat treated 718, see quite a big jump up in performance, but not as much of a jump as up to the wrought strength, which is a little bit disappointing. So then we see a similar story in RE41. See the difference in performance is quite big, not as big as 718, and we think that's due to 718 undergoing quite an extensive aging process to achieve its peak performance compared to the other alloys. And we see H188, which is just our solution strengthened alloy, which is the closest to the wrought strength. And it's a very similar story in the yield strength as well. And on the right here is our Instron 8801 servo hydraulic testing machine, which we use to do the tests. So in conclusion, we had the following results of the study. So we selected alloys that were selected based on the existing data and the suitability to the application. All the alloys were successfully deposited using the WAAM system. And the mechanical testing indicates that the WAAM alloys, there was a correlation between the two precipitation hardened alloys, which was 718 and RE41, and there wasn't much of a correlation between those two and Haynes 188, which was the solution strengthened alloy. Heat treating does increase the strength over as deposited material, which was the biggest difference was seen in Inconel 718 and RE41. And H188 was the closest to the wrought strength, and we think that's likely due to it not being precipitation hardened. And the biggest difference we saw was between Inconel 718 and its maximum performance in the wrought data. And we think that's probably due to the more extensive aging process that 718 undergoes to achieve its maximum performance. And the WAAM alloys in as deposited condition clearly need further post-process to return to wrought strength. So we're hoping to do some mechanical, another mechanical process after depositing, such as rolling or shot peening. And then solid solution strengthened alloys achieve closer to the maximum performance. That was just H188. And here are some references if anyone was interested in finding out more. So thank you for listening, and if you have any questions, I'd be happy to answer them, or you can email me after if you wish. I'm at w.james@cranfield.ac.uk. Thanks again.